Hello everyone, in this video we will learn simplification of Boolean expressions by using KMap. Boolean expressions are used to represent digital system. Question arises, why do we need to simplify Boolean expressions or logical expressions? Let us consider this example. Here we have an expression y equal to a bar plus b, which can be simplified as ab. Now to implement this expression we need these gates. That means total 3 gates are required to implement this expression. However, to implement this expression we need only one AND gate. So thus a simplified expression reduces the requirement of hardware, and thus the overall cost of the system for implementation get reduced. Various methods for simplification of logical expressions are algebraic method, KMap method, and tabular method. In algebraic method, Boolean algebra is used. KMap is a graphical based technique, and we have tabular based method. In this video, we will limit our discussion to KMap only. KMap is a graphical method for simplification of logical expressions. Before discussing how to use KMap in simplifying logical expressions, let us discuss how to construct a KMap. To construct a KMap, we will follow these rules. First one is n variable KMap has 2 to the power n cells. Two adjacent rows or columns must differ in exactly 1 bit position. The cells are labeled with the corresponding row of truth table. The map is cyclic. We will discuss these points one by one. Let us start with a 2 variable KMap. A 2 variable KMap basically represents a digital system with 2 inputs. In the system, we may have 2 input AND gate, 2 input OR gate, or any combination of these kind of gates, but the total number of inputs to the system will be 2. The first rule says that n variable KMap will have 2 to the power n cells. So a 2 variable KMap will have 2 to the power 2, that is equal to 4 number of cells. So this is cell 1, 2, 3, 4. Similarly, a 3 variable KMap represents a digital system with 3 inputs, and accordingly, as per the first rule, it will have 2 to the power 3, that is 8 number of cells. Similarly, a 4 variable KMap represents a digital system with 4 inputs, and it will have 2 to the power 4 equal to 16 number of cells. Let us come to the next points. 2 adjacent rows or columns in a KMap must differ in 1 bit position only. In a 2 variable KMap, we have variables a and b. We can place the variables in the KMap like this: a representing the columns like this, and b representing the rows. Thus, in this cell a is equal to 0, b is equal to 0. In this cell a is equal to 0, b is equal to 1, and so on. Thus, this cell can be labeled as 0, 0 or 0. This cell can be labeled as 0, 1 or 1. This is 1, 0 or 2. This is 1, 1 or 3. If we compare with the truth table, we can see that each cell is labeled with the corresponding row of the truth table. For example, this cell 1, 0 is labeled with the corresponding row 1, 0 of this truth table. In a 3 variable KMap, we have variables a, b, c, and we can place the variables like this: a, b to represent the columns, c to represent the rows. Thus, a, b will have values like this, and c will have values like this. We can see that these 2 columns differ in only 1 bit position. These 2 columns also differ in only 1 bit position. Similarly, these 2 columns also differ in 1 bit position. So we can see this sequence 0, 0, 0, 1, 1, 1, 1, 0 is a gray code sequence. This is followed to satisfy these conditions. Thus, we can label the cells 0, 0, 0 or 0, 0, 0, 1 or 1, 2, 3 and so on. This cell is labeled with the corresponding row of this truth table. For example, this cell 101 is labeled with the corresponding row 101 of this truth table. We can also change the positioning of these variables. We can place A here and BC here. In that case, the labeling of the truth table will be like this: 0, 1, 2, 3, 4, 5, 6, 7. In a 4 variable KMap, AB can be placed to represent the columns, CD can be placed here to represent the rows. Thus, AB will have values like this, CD will have values like this. So thus this cell is labeled as 0, 0, 0, 0 or 0. This cell is labeled as 0, 0, 0, 1 or 1. This is 3, 2, 4, 5, 6, 7 and so on. So we can see here this particular cell corresponds to this particular row of this truth table. In a 4 variable KMap also, we can interchange or we can change the position of these variables like this. In that case, the cell numbering will be 0, 1, 2, 3, 4, 5 and so on. Since the KMap is cyclic, therefore the outer columns or the outer rows in the KMap will be considered as adjacent to each other. To understand, let us see this. So let us see this 3 variable KMap. Here cell number 0 is adjacent to cell number 1 and cell number 0 is also adjacent to cell number 2. Also, since the map is cyclic, cell number 0 will be considered adjacent to cell number 4. Similarly, cell number 1 will be considered adjacent to cell number 5. We can see like this. So here you can see cell number 4 is adjacent to cell number 0, cell number 5 is adjacent to cell number 1. This also satisfies the condition that the 2 adjacent cells will be differ by only 1 bit position. Here you can see cell number 0 has this bit position 0, 0, 0 and cell number 4 has 1, 0, 0, 0. So only the first bit position is different. Now let us see in a 4 variable KMap. Here cell number 0 is adjacent to cell number 4, 1 is adjacent to 5, 5 is adjacent to 7, like that. We can also see, as the map is cyclic, this cell 0 will be considered adjacent to cell number 8. 1 will be adjacent to cell number 9. You can see like this. So this is cell number 8 adjacent to cell number 0, cell number 9 adjacent to cell number 1, 11 adjacent to cell number 3, 10 adjacent to cell number 2. Also, we can see like this. This cell number 2 is adjacent to cell number 0. Cell number 6 is adjacent to cell number 4. 14 adjacent to 12. 8 adjacent to 10. In our next video, we will discuss how to place and group the terms in KMap. Thank you very much for watching.